de hoy. Estamos muy contentos de presentarles a ustedes el gran honor de tener hoy a uno de los grandes de la fatiga y de los puentes en el mundo, el profesor Jamshid Mohammadi del Instituto de Tecnología de Illinois de la ciudad de Chicago. Él tiene una maestría y un doctorado en ingeniería civil de la Universidad de Illinois en Urbana-Champaign y tiene muchísimas publicaciones en el área de estructuras, puentes, conservación de puentes, tiene un libro en conservación de puentes y es miembro vitalicio de la Sociedad Americana de Ingenieros Civiles. En el momento en el que yo salte al inglés, pues el resto de la presentación va a estar en inglés por también el resto de presentadores, perdón, de personas que tenemos en la sala, que es un grupo bastante internacional. Good morning, everyone, and thank you for attending today's the 24th International Seminar Series. And today we're pleased to present Dr. Jamshid Mohammadi from the Illinois Institute of Technology. I had the honor to meet him and had his classes during the time of my graduate students back in the time. And today we're honored with his presentation on bridges and why do they fail. Dr. Mohammadi is currently a professor of civil and a professor in the Department of Civil and Architectural Engineering at Illinois Institute of Technology in the city of Chicago. He's got a master's and a PhD from the University of Illinois at Urbana-Champaign with a specialty in structural engineering. His research involves system reliability with applications to structural failure and life cycle analysis, which is a very important topic for Colombia these days. Among his many publications, he has a book on system engineering, and over several decades, he has taught courses in system reliability, bridge management, systems engineering, and structural design. Also, Dr. Mohammadi is a life member of the American Society of Civil Engineers. So, Professor Mohammadi, thank you very much for being with us this morning. And the room is yours.
Thank you so much, Dr. Federico, and thank you all our colleagues in Colombia, other places. It's really a pleasure to give this presentation. I wish that I could do it in person. I remember my last trip to Colombia when I gave a talk to colleagues back in what I think was 2007. That's pretty much when I met Federico. He was a student attending the presentation I gave at Los Andes University, and there were people from Mariana there. So that friendship started there and continued today. So hopefully one of these days we can visit Colombia again and start our collaboration. So today I'd like to talk about a topic on bridges, and it's actually a down-to-earth type of talk. I mean, it's not very scientific, and simply I just want to say why bridges fail. Most of this is based on my own observation and research with my students or even myself. So please feel free to comment and ask questions. So bridges come in many types and forms and make up of important components of the built environment and infrastructure system. So I like to touch upon an overview of different types of bridges in US, and the types of bridges we use here based on some of the studies that I did with Federico for Colombian bridges are a little bit different. There are some commonalities, but some are different. So I thought it would be good if I introduced the different types of bridges in US and talk about some reasons why bridges fail and go over some examples of bridge failure and explain methods used that we can prolong the life of bridges. So these are pretty much the contents of my talk. So when you look at infrastructure system as a whole, you will notice that under that I put structural systems, environmental systems, transportation systems. And then you notice that bridges would appear in those red boxes in two places. They appear under a structural system. They also appear under transportation system. Of course, we know that bridges offer public and private users the level of comfort and operational safety needed to meet the overall objective of the transportation network. And when you look at a bridge as a structural system, then it comes under the structural systems, of course. However, when you look at it at the network level, then it comes under transportation systems. Of course, the two lower boxes, the red boxes you see, are related to each other, but each of those have their own area of research and investigation in terms of reliability and also contribution to the infrastructure sector system. So what are the types of bridges in US? That's a good question. And you ask people, although they think it's a simple question, but many people just simply cannot answer that question. And then I decided to come up with an answer that what are different types of bridges? So in a broad sense, they are links in roadway and railway system to allow traffic. So based on that, you can categorize bridges, one, based on their type of service and function, and two, based on the type of material used in their superstructure primarily. And finally, based on their geometry. So let's look at some of these. In terms of the service and functions, in the US, we have categorized them as highway bridges and railroad bridges, which are pretty universal. Pedestrian and bicycle bridges, we call them footbridges. Movable bridges, which may not be familiar with a lot of people what these things are. And in terms of other functions, for example, a bridge may be used for a major oil or water pipe, and the bridges that are used in the airport. So here are a few examples. The lower figure to the left is, of course, a railroad bridge, and that's a typical in US truss bridges. Then to the right, you find the modern concrete bridge, and doesn't have much in terms of aesthetic and architecture, and these are very common in US, very flat type of pre-stress or concrete, but at this point, we categorized in terms of the network, so that would be a highway bridge. And then you see to the left is a cable bridge, which is used as a bicycle or pedestrian. And to the right, you find a bridge that is used in an airport. So these are some of the examples in terms of the application or use. And based on the materials, of course, that's a little bit more known to us. However, we have to be a little bit careful when we say in terms of materials, because as you expect, the bridge may not be entirely made of the same material. At least a lot of them in US are like that. However, we are referring to the superstructure. And in that case, we have steel bridges. And again, we are talking about the main girder, because a lot of steel bridges, at least the ones that are referred to in US, made of reinforced concrete deck part. We are talking about the girder part. That could be a truss, or it could be a girder, a plate girder, or a standard W sections or things like that. Then concrete bridges are either reinforced or entirely pre-stressed. We have a whole bunch of timber bridges in US, and we still have a few masonry ones. So these are in terms of the material types. Now, in condition assessment, before I continue, I brought these terms of superstructure, substructure. So for clarification, I put this diagram there. When we say superstructure, that includes the girders, the floor beams, and the deck. And we talk about substructure, that includes abutments and piers. And finally, when we say foundations, of course, that includes footings and piers. So when you look at the longitudinal detail of a bridge, that you see those components explained in here. And lower you have the cross-section of the superstructure. So I thought this would be good to clarify before we continue. Now, in terms of the geometry, in US, we call bridges in terms of geometry either as girder bridges, arch bridges, truss bridges, suspension bridges, cable stayed bridges, floating bridges, that might be a little bit of new to you. What are floating bridges? And another type that may be new to you, to our Colombian colleagues, is what we call covered bridges and timber bridges. Now, these are historical bridges. I show you some photos of those, and they primarily were built in the Midwest area of the United States, in Indiana, in southern Illinois, in around 17th, 18th, even sometimes into 19th century. And now they have a lot of historical values. They preserve them because of their values. So again, going back to the photo I showed you, now you see a classified as a truss and also an arch bridge in this figure. It's a railroad bridge and also a steel bridge. So you can see it gets into different categories. Upper left, you find a suspension bridge, as you're familiar with. Lower right is a bridge in Chicago, is on North Avenue, and this is brand new. I mean, brand new is about 6 years old, and it's a cabled steel bridge. And in US, when we have truss bridges, we have categories and we have different names. Probably the most popular one is the one upper left is called Pratt truss. And then a lot of old railroad bridges, if you look at the middle one at the top, Parker, and then the Camelback are very popular. And then you go further down at the middle, you notice that some of those types are named after cities and states, Baltimore and Pennsylvania. And the ones to the extreme lower right called lattice, those are very rare. I mean, I probably have not seen very many of those. But, these are the categories in case you want to know how in US we categorize truss bridges. And finally, I thought that, again, I'm using these different terms and I put this cartoon together for you to know how we call different structural components in a bridge. This is a very crowded figure, but certainly we have two trusses in orange color, and we have the bottom chord and top chord that you are familiar with. And then you notice that there are some blue beams called floor beams, we call them. And then the green ones that go across called stringers. Then we have bracings at the top. If it is a straight, called a strut. If it is a diagonal, called a wind bracing. And then you notice those green bracings at the top, those small ones, we call them sway bracing. So there are different terms that they use. In case I use these terms, I wanted you to be familiar. And the deck, it refers to the finished part that the traffic is using it. Okay. So again, a couple of more examples. I intentionally put the figure to the left. This looks like a concrete bridge, but in terms of category, we call it a steel bridge because of the steel girder. The one to the right is an all concrete bridge, so that is definitely called a concrete bridge. The one to the left is a pedestrian timber bridge, usually used in amusement parks, in recreation areas. And the one to the right is one of those covered bridges that I told you about. And these are so important in certain areas of Indiana and Illinois that people even have festivals in fall semester called covered bridge festivals. So people gather and, they use these bridges. Sometimes even they use their old buggies and carts, horse-driven carts and things like that. And they are being preserved, and many of them are considered as monuments that needs to be protected. So, of course, you may be familiar with some of these bridges. These are stone bridges. Actually, Minnesota is in US. So these are the arch bridges using masonry materials. All right, now this is an interesting one. It's called a pontoon bridge. It's a floating bridge. And the concept is that you have a series of boxes practically. You see those red boxes? They are floating, and the bridge deck is built over them. Now, you drive over this bridge, you don't even feel that you are on a floating bridge. I mean, they are so stable. And these pontoons are secured to the riverbed or even a lake bed through some bracings and heavy weights, and they are kept in there. They require a very rigorous inspection program. In this case, in this special bridge, they are made of, these pontoons made of steel, just like boats. But there are 4 of these in the state of Washington in US that the pontoons are made of concrete. You know, these are concrete boxes. And you go inside one of these boxes, you don't see any cracks. They are pre-stressed. They are done so elaborately, you cannot have any cracks. The figure you see here is called Lacey Morrow Memorial Bridge. And you notice that in the foreground, it is pretty much like a truss bridge. And then there is a little arch bridge. And then the pontoons starts from around this point and continues. Very stable, nice bridges. Unfortunately, one of these failed, and I was involved in the failure investigation of that bridge. And so we call it was cause of failures, why a floating bridge could fail. They are actually very reliable. And the reason for a failure of the floating bridge there in the state of Washington was neglect. What happened is that these pontoons require that somebody actually go inside. They have a little manhole and a cover. You open it up, you go inside and do inspection, make sure there are no cracks and things like that. And one of the workers forgot to put the cover back. And lo and behold, that night there was a huge storm in the area. A lot of water accumulated in one of those, just one pontoon. It sunk, it went down, and took major portion of the bridge with it. So that was a cause of failure. Now, the study we did was with another colleague. We looked into the sequence of events that would cause collapse of these kind of bridges, and we came up with some recommendations for, of course, for future safeguard against those kind of failure. However, the idea of a pontoon or floating bridge is not new, and I got my background, and then the first floating bridge apparently was built by the Persian king Xerxes. And those of you who are Bible scholars and you know Book of Esther, you know King Xerxes was the king and Queen Esther married him. So he conquered Greece in 485 BC. But first, his army had to cross this Hellespont Strait, which is about 4,410 feet, about 1.3 kilometers wide. So he came up with the idea of using a series of boats to make a floating bridge and pass his army. And this is a pretty famous historical fact. So that kind of bridge has been around for years. How about movable bridges? Well, we who live in Chicago, we are very proud of our movable bridges. We are in North America. We are #1 in terms of having movable bridges. These are bridges that open up, allow the marine traffic to go through. We have about 45, 46 of those in Chicago alone. So if you visit Chicago, if you have visited Chicago or visit, those are among the scenes in Chicago River around the north of downtown Chicago. And at times that the boats go, they open them up. And we call them sometimes bascule bridges. Bascule is a French word and means balance scale. And these bridges practically follow the same principle as that of the balance scale. So you have a counterweight which balances the span when the bridge is upward position. Because of the balance weight, and the bridge really requires little force to open it up. So the mechanism of operation of these bridges is practically unchanged since 18th, 19th century. And I think the largest number of those in any given town is in Amsterdam. So Chicago is like #2 in the world. And you see a very nice photo of what we call a State Street Bridge, which is open, and the marine traffic goes through. If you are driving over the bridge, you have to wait. So there is a sign that you stop, and you'll see like a a room or an office in here. The operator sits in there, monitors and equipment is there to operate it. Further down, you see a second bridge. This is called the Columbus Drive Bridge. And talking about failure, this bridge failed. Not that it came down, it's a very strange. It just went up and stuck on didn't come down. No matter what they did, the bridge didn't come down. So for a period of months, the engineers did a lot of work. This was a failure that was very famous at that time. And it says Chicago is a strange town. When the bridges fail, the bridges go up, they don't come down. So that was back in 1991, 1992, around that time. And the reason for failure was the equipment were rusty. They, did not get enough attention. And as a result, it got frozen up there. So quite a bit of force they had to put together. They had to do some repairs to bring it back down. So now why bridges fail? So you saw some examples I talked about. And although failures in bridges are relatively rare, they sometimes happen and make headlines. That's a problem. When a bridge fails, all of a sudden is a news headline everywhere. There are a variety of reasons a bridge may fail. Often there is a main reason, and this is compounded or superimposed by other factors. So there are always a host of factors, but you can always identify a main item. So here I put 9 different reasons, and there may be others. And the number 1, wear and tear, and they have reached their useful service life. Number 2, design errors, and we'll see some examples of those. These are design errors that are undetected. Number 3, hit by a ship or by a barge. Now, barge are those flat ships that carry primarily garbage and rivers and sometimes coals and things like that. And number 4, bridge is neglected for adequate repairs, rehabilitation, or retrofit. Now, if these terms again are a little bit new to you, what is a repair versus rehab or retrofit? I'll talk about those just for clarification. For a concrete bridge, number 5 can be damaged or deteriorated. Reinforcing bars or pre-stressing wires may be corroded, causing a reduction in its strength. And I have seen that in a lot of box girder bridges, not a lot, but some box girder bridges, that, when the bridge fails, these tendons or pre-stressing reinforcement are pulled out, and sometimes you wonder how much force was there to cause this kind. I've seen some failure cases that are amazing. Number 6, fatigue of steel structural members. This is in the form of a fracture in the metal. And then number 7, error during construction of new bridges and during demolition of old ones. Number 8, unusual loads, such as strong earthquakes, storms, hurricanes, fires. And number 9, terrorist attacks. So these are some of the reasons. Actually, the study and what I did with our colleagues at Javeriana, we looked into causes of failure in Colombian bridges. And I think terror attack was, at that time, was one of the factors, major factors. As you know, bridge design is done per a standard that is recommended, at least in the US, by the American Association of State Highway and Transportation Officials. That's for highways. And for railroad bridges is by the American Railway Engineering and Maintenance of Way Association, called ARIMA. Many types and combination of load conditions are used, and in the US for highway bridges, we use 356 kilonewtons, which is 80,000 pounds as a standard load for bridge design. For railroad design, we use a sample of a train called a Cooper E80, which is a series of loads, concentrated loads with some uniformly distributed load. You put it on a bridge and design accordingly. Of course, there are also a variety of other forces that you consider for design. But although there is always a margin of safety in design, I highlighted that area if a structural member is not designed appropriately and if some unusual load occurs and bridge may fail. So the question is this a common cause? The answer is no. It happens very rarely. And if it happens, it is probably accompanied by other factors such as heavy loads. And let's look at an example of a bridge failure. Some of you may remember this. Interstate Highway 35 westbound, August 1st, 2007, Minnesota bridge failure. This bridge crosses Mississippi River, had 8 lanes, the steel truss arch bridge that carried Interstate 35 west, as I told you, across the San Antonio Falls of the Mississippi River, close to Minneapolis, Minnesota. The failure happened August 1st, 2007, killing 13 people, injuring 145. The bridge opened back in 1967 and was Minnesota's third busiest, carrying 140,000 vehicles daily. Cause of failure? A design flaw caused the collapse. However, this was accompanied by periodic application of the load, so fatigue was also contributing to that. Funny thing is that this bridge was inspected before it failed and nobody detected this flaw in there. It's a gusset plate that when you look at now the photos before the failure, you could suspect that was something wrong with the gusset plate. So it actually ripped along a line of rivets, and the additional weight on the bridge was not a help either, and as a result, the bridge failed. So here are figures. First, let's look at before the collapse. Upper left, good-looking bridge. Some details to the right, upper right, focusing on the gusset plates, you see tons of rivets attaching, these structural members together. Looking at the lower left, the bridge collapsed, is the aerial view. Now I want you especially look at the lower right. And when you look at closely to those gusset plates, you notice that at least the one to the left has sign of buckling. So that means it is deformed. And I'm just surprised that, nobody paid attention to it. Those are the ones that ripped. Another cause of failure, extreme load, hurricane in this case, Hurricane Katrina back in August 29, 2005, caused the failure of this bridge, which is over Interstate 10 in Florida. It was a twin span bridge called the Frank Davis Memorial Bridge. And you can see some of those elements or components have been displaced and causing the failure of this. The lack of proper repair, rehabilitation, and maintenance is another cause of failure. And I highlighted this in the abstract of this talk because this is among the most recent bridge failures. 50-year-old bridge, Morandi Bridge in Genoa, Italy, August 14, 2018. Some of you may remember that. It was a major bridge failure in Europe. The reinforced concrete, pre-stressed concrete had signs of damage, which was ignored again by authorities, although there were several warnings of this. The bridge is one of the major links to France and parts of the European Route E80, and it is in the district of Genoa in Italy. And you see some prior collapse photo to the left and after collapse to the right. Of that bridge was definitely lack of maintenance, proper attention. But before I move on, I thought that I'll bring up some definitions in here because it would be important for my next slide. So when we say maintenance, what are we talking about? This is a scheduled inspection intended to make sure the system has no problems and it functions properly. So that was maintenance is called. When we say a repair, is a series of minor replacements or changes in the system to maintain its intended function. If you do not do these changes, the system is still okay, but not very efficient and will deteriorate fast. So this is a condition we call it functionally deficient if you ignore repair. Functionally deficient. Rehabilitation is a series of major replacement and changes in the system to bring its function to an acceptable level. If you don't do these things, the bridge is not failed, but it's called functionally obsolete. That means you really should not be using that bridge. When we use the word retrofit, this is a series of changes that would improve the system function and bring it to a higher level to meet new demands. So this is different from rehabilitation because you make the changes, you make all the replacements, but the function is now changes. And a good example is to retrofit a bridge so that it would be able to now take care of seismic earthquake loads. In southern Illinois, many bridges are going through this process because when they were designed, we did not know that southern Illinois is a major earthquake area. Now that we know, they are rapidly retrofitting these bridges to make sure that if an earthquake comes, they will be able to sustain the load. So now with those definitions, I'm going to put this graph in there. What is this graph? In the vertical scale, it shows the condition of the bridge. Now, whatever system you want to use, so I'll put the new bridge, I call it good, acceptable, may need some repair, deficient, and finally functionally obsolete, which is the lowest level. We don't want anything below functionally obsolete. There is an sort of like an orange curve, a smooth curve going down. That's the deterioration curve. If you don't do anything to your bridge, its condition starts going down over time, and eventually you get to a case that is below obsolete, and you have to close that bridge and bring it down. The other graph comes along very similar, but then it jumps and again comes down, jumps, comes down, and so on. And this is the green one when you do periodic repairs as required by the bridge. So if you look at the one that jumps ups and downs, there are two significant points. Number one is that you notice that the end life is much longer than the other one. So you have prolonged the life of the bridge. The other notable thing is that every time we do a repair, we go up, but we never reach like a brand new bridge. The second one is a little bit lower. Third one is lower. Why is that? Well, an example, I don't know whether you have noticed or not. In mechanical systems are like that also. Like you buy a new car, right? You put a set of brand new tires on it already, use it for 50,000 miles, like 80,000 kilometers and so on. And then you put a new set of tires, right? You expect that new set of tires would go, again, 80,000 kilometers. It doesn't. It probably goes only 60. So what is the reason? The reason is a wear and tear on the system that are hidden and doesn't let any repair to get back into absolute new condition. So you get to a point that in here, after repair number 5, we have improved a little bit. Beyond that, doesn't matter how much money you put in there. It's no use. So you have to replace the bridge. But the significance of periodic repair is that you have prolonged the life of the bridge. Let's look at some more failure cases. And this one has a lot of historical value. So it's called the Silver Bridge. This bridge was a truss system made of what we call I-bar chain suspension and truss system together, built in 1928. At that time was one of the wonders of bridge engineering. The reason they call it Silver Bridge is because of the aluminum paint they put over it. The bridge carried the US Route 35 over the Ohio River, connecting Point Pleasant, West Virginia, and Gallipolis in Ohio. On December 15, 1967, it collapsed during the rush hour traffic, resulting in the deaths of 46 people. The cause of the collapse was the failure of a single I-bar. Now, I-bars are those connections at the end of a bar. They are round and they have a hole at the middle in a suspension member. Due to a small defect, which was only 0.1 inches. I mean, 0.1 inches, is how much is it? It's like a 2.5 millimeters, very small defect. Anyway, so there was a defect which wasn't detected. That was a cause of failure, plus the heavy load. By the way, this bridge was very heavily loaded. But the main reason for the failure was labeled as poorly maintained. This bridge was totally neglected. So what happened? You see some of the figures prior to collapse, after collapse. Back in 1967, because of the collapse of this bridge, the United States mandated inspection of bridges once every 2 years. So every highway bridge in the United States must be inspected once every 2 years. So that started back in 1967. Lyndon Johnson was the president of the United States who ordered that to be done, and it went past the Congress quickly. So metal fatigue. Metal fatigue is another cause of failure, and this mode often happens in structures that are periodically subject to loading and unloading, and bridges are examples. Now, again, you're familiar with fatigue, but I always bring up this paper clip examples. If you want to break a paper clip, what would you do? You just bend and unbend and bend and unbend. You put enough stress in it that you break it. So, of course, in bridges, we do not stress structural components that severely. We don't stress them beyond the yield level. Here is example of cyclic loading when your loading goes well above the yield. You know, you have a little bit of permanent deformation, epsilon1, and then next cycle epsilon1 plus epsilon2, etc. Eventually, you reach epsilon u. Beyond that, you know, you break, and this is an abrupt brittle type of failure. In highway bridges, we have done some tests on Illinois bridges. Actually, the stress for most bridges, hardly 27 to about 34, 35 megapascal. It's not that high. When a truck comes, you see an example of the most of the truck traffic in US. This is an 18-wheeler, 5 axles, 80,000 pounds, which is 356 kilonewtons total weight. So that's the major portion of truck traffic is that. One of these goes over the bridge, you see a rise in stress, and it comes down. The amount of stress that you see, the maximum, sometimes we see isolated cases of going higher than that. But of course, it's also the level of stress depends on the speed of the truck. We are talking about 55, 60, about 80, 85 kilometers per hour. And why the speed of the truck is important in the stress level? Because of the road roughness. The faster the truck goes, you know, it would be like more like having a more frequency of the load. You know, the frequency goes up. And as a result, you come up with the higher stress levels. But the ones that we measured in Illinois for most steel girder bridges were hardly 35 megapascal. So what's the consequence of fatigue failure? It's an abrupt failure. It is a brittle failure. It doesn't give any warning. The only way you can prevent it is simply by periodic inspection, by careful inspection, looking at the critical sections. Most critical sections for fatigue are welded components. And in US, we use a detail. I didn't show the detail in here, but we use what we use is called the cover plate. Is welded at the bottom of a flange of a steel girder, and that's where the fatigue usually starts. So let's look at some examples of bridges, some very recent and one very old. So Florida International University, you guys might remember that, a pedestrian bridge collapsed during construction, 15th of March 2018. Concrete pedestrian bridge. This was supposed to be a bicycle pedestrian bridge connecting two parts of the campus. Beautiful bridge. They were using a method called accelerated bridge construction. Cause of failure, still, I haven't been able to find the report that gives me exactly what the cause is. My own idea is that they rushed into finishing this bridge. They were using a lot of publicity about how beautiful this bridge is and how this accelerated method is effective. And, I think this was uh, rushed into opening this bridge, or, at least the opening the forms, because it came pretty much under his own weight. There wasn't any type of extra load on it. Unfortunate thing is that there were students and people in the traffic jam in the underpath, and some of them lost their lives. And Interstate 10 in Southern California partially collapsed in 20 July 2015. What was the cause of that failure? That cause of failure was attributed to scour. Now, a scour is a washout, rivers washing the piers and things like that, causing instability. And number 3, a bridge in Scott City, Missouri collapsed on 25th of May 2013. A Union Pacific train T-boned, just perpendicular to another train, a Burlington Northern Santa Fe train outside of Scott City, Missouri, and approximately 2:30 a.m. The impact caused numerous rail cars to hit a support pillar of a highway overpass, collapsing two sections of the bridge onto the rail line. Division Street Bridge, this is an older one. Spokane, Washington, collapsed on 18th December 1950. It was a steel bridge for trolley cars. It collapsed a week after, now listen to this, being resurfaced. Cause of collapse, poor steel, metal fatigue, and a previous impact by another bridge swept downstream during a flood. So you notice that the fatigue was mentioned there. Now, this is a important failure, Quebec Bridge, Quebec City, Canada. I always bring this as a case study to my students, especially when we talk about ethics. This happened on 29 August 1907. It was being built using what we call a cantilever system. I mean, two parts of the bridge starts from two ends, and then they lock them inside at the middle when the bridge is completed. The reason for collapse was nothing but miscommunication among different parties. I mean, miscommunication doesn't cause a failure. It was overloaded conditions, but this was detected by a junior engineer there. And he continuously used at that time telegrams to tell the designer, Mr. Theodore Cooper, who was a very prominent bridge engineer of the time. Mr. Cooper, please come over and look at it. To me, this bridge looks like overloaded. I see these cantilevers are vibrating very rigorously. What am I supposed to do? Should I stop the construction? Telegram comes back. I have so much confidence in my design. Proceed. You don't have to stop the construction of the bridge. So this miscommunication, and practically at one point, Mr. Cooper decided not to even answer anymore. And this bridge unfortunately collapsed and caused many lives. So we bring it as a case of ethics. Mr. Cooper did not design any bridge after that. He was under so much stress after that failure. Anyway, how can we prevent failures? Certainly proper design is important, proper quality assurance at the time of construction, paying attention to details, good communication between all parties, and this is very important. Periodic maintenance and repair as needed. This is especially important for bridges that are exposed to weather and may be subject to fatigue and corrosion. In the United States, every highway bridge, as I said, must undergo a visual periodic inspection once every 2 years by a qualified person. A qualified person is a trained person, and the standard of the practice is that the inspector notes any damage, wear and tear, missing elements, cracks, etc., and rates. Now use a sort of rating for the components and for the entire bridge. We also do rating for superstructures, substructures, and so on. So Federal Highway Administration uses 10 levels of rating. If the inspector finds out that the bridge is absolutely in excellent condition, gives a rating of 9. And then you go further down. For example, 4 means poor, advanced section loss, deterioration, spalling, or scour. And if he gives a rating of 0, that means the component is practically failed. And when we use these, we use some sort of integration of these ratings to come up with a rating for the whole bridge or segments of those. Usually, if it is a rating of 4 or below, we just do not trust that bridge. We have to do major work for that bridge. Other agencies like railroad people do not use these. They use like either 4 or 5 categories, but very similar. So we did a research study because these ratings are subjective, right? You send somebody goes and write a note. So we were wondering whether this is reliable because, you know, sometimes you send an inspector and he gives a rating of 6. The next year, the same component, but a different inspector will give, no, this is a rating of 8 or 7. So we have this discrepancy, but very interesting. We looked at so many years of data. A couple of students of ours and a colleague of mine, Professor Arditi, and myself did this study. We noticed that really these ratings do make sense. They pretty much show the deterioration of a bridge. You know, I apologize for it's not too clear, but those are not important. If you look at how the bridge deteriorates, you notice that it follows what you expect. Goes from 9 and you are getting around here that you're saying, okay, stop it. You have to do something to this bridge. So, you know, these are for all bridges. This is only for the components of the bridge where we saw this similar trend. So the what we call visual inspection is a very effective way of following up what's happening to bridges. Accompanied the visual inspection is another method called analytical rating in US, and that one is done by computation, calculations. The equation is fairly simple. You really use the capacity, deduct from the capacity the dead load effect divided by the live load. And when it is accounted for the dynamic effect. So that's the general equation. If the rating is smaller than 1, it means the component is not acceptable. You can do this for bending moment. You can do it for shear. You can do it for fatigue. And then you can also have 2 categories, operative or inventory, for the purpose of everyday use or for purpose of record keeping. So, and there are actually very famous programs that that is available in US called PONTIS, which means bridge, of course, in your language. Nowadays, we use the method called load and resistance factor rating, LRFR. So the equation is pretty much the same. I mean, it's expanded. Rather than capacity, we use a C. We use a series of load factors as shown with gamma. The dead load is divided into 2 parts. DC is a dead load effect due to a structural components. DW is due to the veering surface. And then you might have an unusual load, is a plus or minus because sometimes it's upward, sometimes downward. But the denominator is exactly the same, except that the load factor is applied. So this is the equation which is now used. We actually did a study trying to correlate in visual inspection with analytical inspection. There is no linear correlation. However, through some advanced method like fuzzy logic, we were able to find some correlation between the analytical versus the visual inspection ratings. Anyway, load testing. Load testing is also becoming very popular. It is another way of understanding the condition of the bridge. Bridge load testing is used for condition assessment. It is, of course, costly, requires money, and we do it in situations when extra costs rather, really require this kind of testing. Usually a truck of known weight is brought to the bridge, and using sensors, stresses are obtained and used to determine the capacity of the bridge. So it's, in principle, it's very simple. There are two different types of testing: proof load testing and diagnostic load testing. So what are these two? Proof load testing is used to demonstrate that a given bridge can carry the legal truck load prescribed by the code in a safe manner. So a truck of a weight equal to the code, for example, the 356 kilonewton. You bring it to the bridge at a given speed, usually 30 miles per hour, which is about 50 kilometers per hour. If the bridge can carry this load without signs of distress, of course, you do complete inspection, then you have rated the bridge. So you know that the capacity of the bridge cannot be lower than the weight of that truck. Diagnostic load testing is more involved. It is more expensive. You need to put sensors on the bridge in different structural components. Again, you bring the truck, you pass it over a known weight, and now the sensors, they pretty much tell you exactly what level of stresses you have developed. Usually use this method to calibrate the rating equations and make sure that components are not distressed. So again, if you want to know what is the cost, usually anywhere from $20,000 to about $150,000. That would be the cost in terms of labor, sensors, and closing the bridge to traffic, etc., for doing one of these tests. So it's pretty expensive. So going back to that diagram again, now you understand the diagram better. I intentionally put it back again. This kind of diagram is very, very important. And this type of information now we are using to predict and to optimize that when would be the good time to do the repair number 2 or number 3. But through optimization, by timing of this repair, and a couple of students of mine and a colleague that Mr. Guralnik, we did studies and we were able to even minimize the cost of repair, prolonging the life of the bridge systems. So in conclusion, we'll right on time. We have about maybe 8 minutes for questions. So bridges fail because of a variety of reasons. In addition to proper design, a complete program of periodic inspections, load testing, rating computation, timely repair will prolong the life of bridges. Thank you so much for listening, and I'm happy to answer any questions. And of course, Federico, you have to help me if the questions are in Spanish.
Absolutely, Professor Mohammadi. Thank you very much. And I'm going to say this in English and then Spanish at the same time for those who do not speak in English. And then I'll try my best to translate. So if you have any question, okay, the Professor Correal from Andes University raised his hand. Professor, go ahead.
Do you hear me?
Yes, sir, we can.
Okay. Hi, it's nice to see you. I think we met a couple of years ago here in Bogota. So it's good to see you, Professor.
Yeah, I remember. Yeah.
Well, we actually with Universidad Javeriana, we are working together in a very interesting project regarding the develop of a bridge, bridge management system that actually incorporates a lot of things that you are saying. So it's very helpful to hear all of things that you are saying about that, because can help us a little bit to understand what is that in US is doing and what can we implement here in Colombia. Mm-hmm. So I have a couple of questions, and I made this short introduction just to let you know that we are doing that, and my questions are in that way. So the first question is regarding the inspection. in the inspections of the bridges in US, you said that is every 2 years.
Correct.
And they have a very like a person that are qualified to do that. Here in Colombia, we are in the process to have this system, and one of our ideas is that we are doing a very quick inspections and let us know when we have to do like very detailed inspections.
I see. Yeah.
So in order to, as you know, here our resources are much less than in US. So this is one of ideas that we have. What do you think about it? If this is going to be possible?
Yeah, actually, this has been also, thought about it in US because of, again, the main reason is the lack of resources because you're talking about, 600,000 bridges in US and the state of Illinois alone, we have 35,000 bridges to be inspected once every 2 years. Involved, but because the law requires, so some states actually do this, and it's very similar to what you're saying, Professor. They do and look at it, and then they say, okay, we don't see any conditions have changed, therefore they defer it for the next 2 years. So, and that has been to a certain extent effective. And again, you have to pretty much rely on the expertise and the level of experience of the inspector. And usually these are experienced inspectors. They look at it more like a cursory, but then they do it a lot more in buildings. There is a parallel in building inspections for facades. In those cases, there's actually a rule in there that you do a cursory inspection. You simply look at it by binoculars and they say, okay, everything is good. Let's postpone it to another 2 years. But in bridges, it's done not formally, but sort of informally by some states. They have been doing it. Yeah.
Okay. Just two more questions. I'm just gonna leave you alone. Sorry.
Go ahead.
But
Sure.
it's a good opportunity for us. And regarding that part of this on the inspection, something that we are done actually is try to take out of the methodology the expertise of the inspector. So that we're doing really is preparing like an app. So the people are going to the field, take all the details of damage that are like in an app, so he can register all the damage, and then the program is going to rate with base of those damage and the area of damage and the damage depends if this is an important element or if it's in the carpet of the road or in the road of the bridge.
I see.
We take all of these damage and then we make the rating. Do you see something like that is
well? I don't think that is into that extent is done because I know that the mandate, the rule that was put together back in '67 requires that a person be there and touch, be very close to the system for bridges. So I'm sure there are some automation, some, electronics way of recording that, but I am not too sure or familiar whether there is that kind of applications in US. But I know for a fact that, the method is pretty much the same. So it does not allow, unless this qualified inspector very closely climbs up, look at the component, and maybe they would enter it through an iPad or something like that. But with the exception of the analytical rating, which is done through applications, I think the visual inspection is done the same way that was done in the past. Yeah.
Okay. And my last question is regarding something that you emphasize twice, that is the degradation, this curve that is doing the degradation, and it's a key part in a system, in a bridge system, in order to know when we have to repair the bridge and try to long the life of the bridge. Right. So here, of course, I saw very quick, and you are having data from the, I don't know, 80, 90 years or something like that. So it's a lot of years. Yeah. So of course, we don't have that data. So something that we are thinking is to take that data that actually is from US, which is very, very well prepared and very well getting, so, and try to adapt to our country. Do you think that could be possible?
Well, the only concern that I have is the differences in the types that we mentioned. I intentionally talked about different types so you guys would compare and see. So if that element is taken out, the type of the bridge and, the traffic in here in US and the road roughness. So these are many different factors that would be, I think, somebody to look at before you can use those things. Certainly, you can adopt those and still use it, but with some modifications. I wouldn't really simply just use the US data for Colombian bridges without looking into those factors, the traffic, the road roughness, and also the type of construction that we use here. Yeah.
Okay, so you recommend to some experts
Right,
look
right,
at
definitely.
data and try to evaluate it and
Exactly. So to
okay.
use some sort of what would be, if you have to use some modification factors, I mean, certainly. I mean, just like if you, a lot of my students, I had the students in Africa, and he said, I have to design, a concrete system in here, and the only thing I have is a US code. What am I supposed to do? So I said, well, do not use the 1.6, 1.2 load factors we use in US. Use twice as many as much, because you are not sure about the quality in there. So, I mean, the same thing. You have to find out what should be a correction factor that we can apply. Yeah.
Okay, great. Thank you very much, Professor.
Thank you, and nice meeting you again. Thank you.
Thank you, Professor Corral. Dr. Hademi, you're next.
Thank you very much, Professor Mohammadi, for such a nice lecture. I really miss those days of being in your class and the way you easily explain hard concepts to be understandable to your audience.
Thank you.
You're welcome. I have a question which I would appreciate your response. In standard manuals, there is a lifetime defined for bridges. But in real life, we see bridges have been kept more than their lifetime, and companies try to keep those bridges as much as possible due to high cost and difficulty of replacing the bridges. Right. They try to do so by repairing the bridge or proposing strengthening for those bridges. My question is it better to increase the lifetime of those lifetime of the spans in those manuals to a more applicable one that we see in real life, since the lifetime mentioned in code books is not consistent with the lifetime of the existing bridges, or at least can we propose some correction factor in those manuals for this type of situation?
Well, I wouldn't recommend changing, because the life expectancy specified is just, a symbolic value. It's for comparison purposes, and the issue is that we need to look at design more, I would say, like a big picture type of thing. And I think that's coming up. I mean, in design of the futures would have all elements of design, not necessarily simply checking a structural component. But as Professor Corral mentioned, you look at the deterioration curve of bridges and put all of those at the time of design. The 75 years, for example, if suggested, that's just symbolic. We are not going to do anything to it, and I don't think it's needed to be done. But we have to look into pretty much do the design holistically, not only looking at the component for the load, but also look at all the failure components, look at what are the requirements for the repair and maintenance, and put those are into factor at the time of design. Only when we do that, then we can come back and say, okay, symbolically 75, but if the bridge is designed with all these factors included, including potential for future, implementation and spending money on repair, then the life could be multiplied by these factors. So that only when the correction could be implemented. But I think we are very far from that point.
Yeah, that makes sense. Thank you very much for your response.
Sure.
Thank you, Dr. Hademi. Is there any other question of the people that we have right now with us? You might be free to speak up in Spanish, and I'll translate it for you in case you don't feel confident. Or you can go ahead and try your English skills. No problem. We're not going to say anything about it. Just go ahead. Yes, Professor Mari Gonzalez, you're next.
Okay, good morning, Professor Mohammed.
Good morning.
I will very happy with you in this conference. Okay, my question. Colombia is a country with high seismicity. I would like to know some recommendation for the design with the use of viscous dampers for bridges.
Okay, so Professor Gonzalez, if I understand, you're talking about for seismic, are you talking about earthquakes?
Yes, about the
All right.
viscous dampers.
Viscous dampers, right, right.
Yes.
Well, you know that in U.S. Universities in California and Nevada, they have done studies on those. Yeah, I have not seen that much popularity as it is in the case of buildings. And I think the reason for it is because most of the earthquake issues for bridges is at the foundation, at the piers, not on the superstructure. So, and then, applying these dampers is not as simple as when you do it for buildings. So certainly that's a possibility. I have not seen being widely used or recommended. And, so that is certainly somebody to look at in terms of, I think the primary factor, Professor Gonzalez, is mainly the cost benefit type of things. You need to find out whether the extra cost justifies it. But there are other methods that we use. The idea is rather than putting dampers, if we can increase the ductility of the piers, right? And the abutments, we pretty much do the same thing by providing additional ductility. So there are a variety of cheaper methods we use. For example, they use special wraps around them, confining piers with tubes and that increase the ductility. So those are the things that they use more often than using dampers. The newest technology is using the shape memory metals for reinforcement at the connection of the foundations to the piers to give that extra ductility. So they are more going to those routes. I know that back in 80s and 90s, there were a lot of studies on viscous dampings for bridges, but I haven't seen much, being used. I see a lot more these kinds of other applications.
Thank you.
Thank you.
All right, and I know we're a little above the time, Professor Mohammadi, but this is an opportunity for us here. I mean, we don't have you every morning to have a nice conversation. I mean, the moment you're here, maybe we're going to ask you more questions and invite you for coffee because, like I said, you're most invited to visit Javeriana University. Let's wait for this pandemic to finish so we can go again back in an airplane and we feel safe back in those guys. I have one final question, Professor, and it's something that has always been on my mind. Those people that are doing the visual inspections, the inspectors that are all the time basing their judgment on those tables that you show 0 to 9, 0 to 10. How do they become so good? I mean, what's the minimum background or preparation those people have to in order to be called? I am a bridge inspector. What do I have to be? What's my background to be there, or is this just a normal pedestrian that one of these days realized, hey, I want to be a bridge person. I want to help with the visual inspection. What do these people need to be called visual inspectors?
Well, actually, in terms of the background, education, I don't think there is any minimum, as long as you have some education level, you know, maybe even 2 years after high school is fine. But they go through a rigorous training. You know, like in the state of Illinois that I'm most familiar with, there are manuals for bridge inspections, and these are big volumes. It's like a, you know, in detail, familiarize them with individual details. It's a lot in there. Familiarize them with some structural concepts, familiarize them with different types of, you know, scenarios, and then that's not only the things. After they go through this rigorous an examination, they become qualified. And when they are young and when they are, you know, inexperienced, they often accompany somebody who is more experienced. And then I forgot the frequency of recertification, but they need to get this recertification once so often to go through again classes. And I have attended some of those classes. You know, not that I wanted to become a bridge inspector, but, you know, a former student of mine invited me to go to Illinois Department of Transportation and attend those. And I saw the level of rigor, you know, of, you know, the materials that they give. These guys are very experienced. I mean, they are like as good as any structural engineer. So, you know, as I said, is after all, they are human. They may make a mistake, or sometimes they have a judgment that is, you know, a bridge that last year was 5, now is rated as 6. That happens, but that variation, as you saw in my research, it actually dissipates when you look at the overall. You notice that it's a very reliable result. So yeah, to answer your questions, they get a lot of education and then they get certification. So.
Good, good, okay. Because like Dr. Correal said, we are in the process here, and we're wondering what's the best for what we have right now. I mean, do we have enough with what we have right now, or do we have to start doing kind of like a night owl school to prepare these people to be ready to go out and face these things just specifically on the field? I mean, is it enough or is it not enough? So we're raising these questions.
Yeah, I
well,
think
Professor.
yeah, definitely this education. By the way, one element of education, sorry, we're running out of time. One element of education they get is safety. This it's really a dangerous job because they have to, you know, climb up. Now, people are thinking to use drones and that kind of thing. So those are also coming into the picture for bridge inspection. I don't know the extent of application, but this is a dangerous thing. So safety is also another that please keep in mind when you train your people. Yeah.
Yeah, that's right.
Yeah.
Well, Professor Mohammadi, thank you very much for being with us today. And everybody with us, thank you very much. A todos, muchas gracias por estar con nosotros. Ha sido un placer y los invitamos a la próxima presentación del Seminario Internacional de la Universidad. Dr. Mohammadi, thank you very much for your time. I'll share the video with you. Thank you, sir, and have a good day.
Thank you. You too. Take care, everybody.
Bye-bye, Professor.
Bye. Bye.